Okay, so this is a mini lesson for standards 8.EE.3 and 8.EE.4. These both deal with scientific notation, but this first standard, EE3, deals with estimating scientific notation. So we're going to estimate scientific notation. And it might be worded in ways such as estimating a number or comparing two numbers. But we can use scientific notation for very, very large or very, very small numbers. So this first one asks for an estimate of 7,625,750,263. So when we estimate it, we can just round. So I'm going to go ahead and look here at this 7 and say the digit to the right of it, that's 6, we'll make it round up to an 8. So it's like an 8 followed by 9 zeros. So I'm going to write it in scientific notation. 8 times 10 to a power, and it's just going to be a matter of counting how many places the decimal moved. It started out here. We're going to move it behind the 8. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So it's a very large number. So 10 to the 9th power would be 1 billion, times 8 would be 8 billion. And so this is our number, answer choice D. Number 3, which number is the best estimate of 0.00003,762? So I'm going to look at this 3. That 7 is going to make it round up. So I've got 0.0000, about 4. And so when we write this number out, we get 4 times 10 to some power. Notice that the decimal here is going to move behind this digit 4. So I'm going to count 1, 2, 3, 4, 5 places it moves. So we've got a 5 for an exponent. But this is a small number, so it's going to have a negative exponent because it's going to be a number such as 0 point something. It's going to be less than 1. So that'll make it have a negative exponent. 4 times 10 to the negative 5th power. Answer choice B. Number 7, a human blinks 9,460,800 times per year. A dog blinks 1,861,440 times per year. About how many more times does a human blink than a dog? So first of all, we see about. It tells us we're just going to get an estimate. But when we see that phrase, how many more times, how many more is going to compare, but how many more times is going to indicate comparing multiples. So we're dividing. We're dividing humans then dogs. So we're going to take the human number and divide by the dog number and see what we get. I could go ahead and use scientific notation. I could just divide these two numbers in my calculator. Either will be fine. But I'm going to say that first one is about 9 million divided by about 2 million. And I'm going to get 4.5. That is very close to C, answer choice 5. You could have actually divided the numbers and could have swapped to scientific notation. Sometimes you just read the problem and see what makes sense. Okay, so now we're to standard 8.EE.4, and remember that we previously said in this lesson that both of these standards deal with scientific notation. The first one really more so deals with estimating, and then this standard is actually calculating with scientific notation. We're going to be precise. So let's look at this first problem. How is this number written in scientific notation? So, just like we did on the estimating, we're going to take our number and we're going to look at this place value and we're going to put a decimal behind it. So I'm going to move this decimal 1, 2, 3, 4, 5, 6, 7 places. Now I'm not rounding, so I'm going to keep 4.28. I'm keeping every digit there that was not just straight zeros. And I'm going to multiply it by a power of 10. it moved 1, 2, 3, 4, 5, 6, 7 places. And it was a very small number, so it's negative because it was less than 0. So we get 4.28 times 10 to the negative 7th power. You might wonder about this problem, why it does not work. Besides the fact that it should be a negative there, it's also got a problem. It's got 0 point something. And this factor right here needs to be a number greater than 1 and less than 10. So in other words, it's just a single digit in front of the decimal, but it's not a 0. Number 5, we're going to express this number in scientific notation. Okay, it almost looks like scientific notation, but then we notice it's 0 point something. So let's correct it. We're going to move our decimal one place right, so we get 3.07 times 10. And this could get a little confusing because we've got to think about which direction our number is going to go up or down for our exponent. But since the number, this first factor, got larger, then our power of 10 should be smaller. It should be to the negative 9th power. But I could check it. Here's what I would probably do if I were working it out and I just wanted to be sure, because this is not a complicated problem to go to your calculator. I'm just going to go to my calculator and type it in. So I'm going to type in 0.307 times 10 raised to the negative 8th power, and I get this decimal, 0.1234567 8 zeros followed by a 3. And I'll go ahead and just check this other one and see in the calculator what it comes out to. 3.07, just because I want to be sure, times 10 raised to the negative 9th power. And I also get 0 point followed by 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and then a 3. So they are the same. They're equal. And so we did get that first answer choice, and it is correct. Number 15 is a word problem. The mass of a water molecule is 3 times 10 to the negative 23rd grams. What is the mass of 50,000 molecules? So we know the mass of 1. We want to know the mass of 50,000. So this problem, ignoring the scientific notation part, let's just think. If we knew the mass of a water molecule was 1 gram and we wanted to know the mass of 50,000, we just multiply by 50,000. We're doing the same thing here. We're going to take the mass of 1, 3.0 times 10 to the negative 23rd grams, and we're going to multiply by 50,000 because there's 50,000 molecules. And so we can just go to our calculator and type it in, and it will give you 1.5 times 10 to the negative 18th power in your calculator. And that matches answer choice B.